Hi guys, sorry about the delay. Sorry, having some technical issues at the minute. I've been trying to get my calculator working in that portion of the screen that it usually sits in, and it's just not wanting to play today. So we're going to have to carry on without it. But I will try and talk you through all the steps, even though you can't see the calculator. Actually, I can't use that calculator at the moment. It just will not appear. All right, so let's get stuck into this question for complex numbers. Just sort myself out so that I can see the chat. If anybody jumps on, feel free to say hello. I better just quickly do a sound check. I can see there we go. All right, so if you're here watching live, just give me a hello. It'd be nice to hear that somebody's out there. Otherwise, if you're watching this back as a recording, then enjoy. Okay, so we have this complex numbers question. Prove that the roots of this equation here are always real for all values of c. All right, now for us to think about roots, we are thinking about the discriminant. Okay, so in this instance, if we want the roots to be real, the discriminant will be 0 or greater than 0. Oh gosh, technology is not being my friend today. Here we go. So we want b squared minus 4ac is going to be greater than or equal to 0. Now in this case, b squared will be the 2c plus 1 part, minus 4 times a, which is 3, and the c is negative c plus 3. And we want that to be greater than or equal to 0. Okay, so now we've got, if we expand out that bracket, we have that becomes 4c squared plus 4c plus 1. And then this other part, we will, we've got the negative c times the 12 on the outside, which is also negative, so that'll be a plus 12c, and then 12 times 3 makes it a minus 36. Actually, no, sorry, plus 36, because we've got minus 3 from this being outside the bracket here, and then times by the minus 12 just here. And we set that, well, actually, no, we're not. We're just going to see what that comes to first of all. So, in fact, let me just write that over this side here, because that's what b squared is, that portion there, and we're saying what it's equal to, and my aim is to show that whatever that comes out to, it will always be positive or greater than or equal to 0. All right, so carrying on with this trend then. So I just had a notification pop up, just check that. All right, so we've got 4c squared. We have 4c plus 12c, that's 16c, and then we have 1 plus 36, which is 37. Now, if we do completing the square on this, it's a way to put this into a form where hopefully we get a bracket that's always going to be squared, and we can show that that would always be positive. To do completing the square, I'm going to take out a factor of 4 first, and I'm only going to bother with the c terms here. Now we do completing the square on those c terms. So we have c plus 2 all squared. Now that will give us the c squared plus the 4 squared, the 4c, but it will also give us 2 squared out of that, so we need to subtract that. So take off the 4 and then add the 37 back on. So now we're looking at this being 4c plus 2 squared minus 16 plus 37. So minus 16 plus 37 becomes plus 21. Now c plus 2 squared is positive, for any value of c. Okay, so whatever we put into c, if we add 2 to it, whether it's negative, positive, whatever, we're then going to square it, so that will always become positive. Which means that if this portion here is always positive, and then we times it by 4, that's going to stay positive, and then we add on 21, that will also stay positive. So c plus 2 squared plus 21 is greater than or equal to 0. So b squared minus 4ac is greater than or equal to 0. Therefore, the roots are real. Okay. Right, let's get the next one up. One moment. There we go. Right, we're on the differentiation page. Okay, now we've got this question where we're finding the values of x where the tangent to the graph, so that means the gradient of the curve is parallel to the x-axis. So that means that x will be equal to, the gradient equals 0 if it's parallel to the x-axis. Now we have to find the gradient. Okay, so we're doing the gradient of this f of x function, so that's f dash of x. This one I'm going to use the quotient rule for, so we have something on the top, something on the bottom. In this case, u is x plus 4, v is, I'm going to multiply it out, x squared minus 5x, because multiplied out makes it that little bit easier to see what to do to differentiate it. Just for the sake of completeness, if I was to differentiate u, I'd get 1, and if I differentiate v, I'll get 2x minus 5. Right, now, f dash of x, put that together in our quotient rule formula, which you can find on the formula sheet should you need to. We're starting with v and timesing it by du, so that's x squared minus 5x times by the 1. Now we will subtract u times dv, so that is x plus 4 times by the derivative of v, which is 2x minus 5. That will be all over v squared, x squared minus 5x all squared. Next stage is to set that equal to 0. So if we want the gradient to be equal to 0, I'm taking this gradient function, set it equal to 0. Now, if I was to bring that up and multiply it across on the other side of the equals, that would become 0. So I can just carry on with the numerator, x squared minus 5x minus, expanding that bracket, we've got 2x squared plus 8x and then minus 5x, so that's plus 3x minus 20 equals 0. Okay, x squared minus 2x is minus x squared. We have minus 5x minus 3x is minus 8x, and then plus 20 equals 0. I prefer to think of things in terms of positive x squared, so I'm just going to reverse all of those powers. So we have a positive x squared, a positive 8x, and a negative 20. Now, that one factorizes. We have x, what would this be? Yeah, x plus 10 and x minus 2. So x equals negative 10 or 2. Okay, I'd forgotten the first question. I'll go back in a second, but just looking up where the achieved point was there. So on the differentiation one we've just done, let me just find the mark scheme there. Okay, so yeah, the achieved on this one was to get the correct derivative. So this bit here, that's where the achieved point is sitting. Now if I go back to complex numbers, and we'll look up that one. Let me just find the mark schedule. Okay. The achieved happened just here. So that bit there, that's where you could get achieved. Okay, on to integration. Okay, just get set up here. Right, here's our integration question. I'll just make it big and then I'll need to just move that off the screen to be able to write in a second, or rather I'll shrink it down a little bit. We've got this curve here, and it's being enclosed between the lines y equals 0, that's just the x-axis, and 2 and 5, we want to find this area underneath. So we'll find the shaded area of this curve here. All right, let me just shrink that down a little bit and come in here. Right, the first thing I'm going to do is rearrange the equation. I'm doing this by a bit of algebraic manipulation or algebraic juggling. If you want to look up a video on how to do it, I've called it algebraic juggling. You also could use long division, and I have a video on that as well if you need to check that. But how this works is we are using the denominator and then turning the numerator into things that use that as an equivalent. Now if I put x plus 3 on the top, that will give me 5x plus 15. So that's 15 more than I wanted. I just wanted the 5x from there. And then we put the minus 3 back on. So minus 15 take away 3 is minus 18. Now the reason I do that is because I can then separate this out into being 5x plus 3 over x plus 3 minus 18 over x plus 3, and you can see those x plus 3's cancel, so we're just left with the 5. All right, so the area is to find the integral of that function. We've now got it in terms that we can integrate quite easily, and we're doing that between 2 and 5. So 5 integrates to 5x. 1 over x integrates to natural log of x, so we bring the 18 out, then it'd be 1 over x plus 3, so that'll be the natural log of x plus 3. Sub in 5 and 2. So we get 5 times 5 minus, hello Stacey, 18 natural log of 5 plus 3. And I'm just going to move over, we don't really need that picture too much anymore. Take away if I sub in the 2, so 5 times 2 minus 18 natural log of 2 plus 3. And then you'll go and pop that into your calculator. I can't show you the calculator at the moment, it's just not wanting to work with me at the moment, but if you pop that into the calculator, then the whole thing comes to an answer of 6.54. I don't think we had any units there, so you don't need to write this, but we generally just write units squared for completeness. So whatever the units are being measured in, we're going to do that squared because it's an area. All right, now where the achieved part was on that is the correct integral. So this bit just here, that's as far as you needed to get for achieved. Okay, so once again, there's your 3 merit questions done. Thank you to Stacey for saying hello and letting me know there's somebody actually out there watching it. For those that are watching back the recording, good luck with it. Make sure you go back and watch the other videos too and do all of that merit practice. And that's us for today. Apologies for the slight technical issues that delayed me getting started and stopped me from being able to show the calculator. Fingers crossed I'll have that sorted by tomorrow's. If you want a head start on the questions that I'm going to use tomorrow, I'll put them together and stick them up on my Instagram page if you want to check them out and have a go before I actually go through them. Not sure of timings yet for tomorrow, but again, I'll post that as a scheduled live so you can come back and check when I'm planning to be on. Okay, see you again.